Welcome to talk number 2 of session number 4. Our talk will be by Eduardo Silva, who will be telling us about Poisson boundaries. So go ahead.
Thanks, Alex. Yeah, sure. So first, I'd like to thank the organizers for inviting me to this very unique event. So yeah, I want to speak about geometric group theory, more from the probabilistic or dynamical systems point of view. And the way that we will do that will be through this theory of Poisson boundaries, right? So I will start by explaining a bit of the context for this theory. Start by fixing your favorite group, okay? Now we'll work with countable groups, but you can do the theory more general. And fix a probability measure there. Okay, so if you like finitely generated groups, you might think that is some finitely generated group that you like, and that mu is a uniform probability measure on a symmetric generating set, for example. But really, we care about more generality. Mu will not need to be symmetric, so the measure of G may be different from the measure of G minus 1. And also, it may be infinitely supported, okay? And you really should think of this as generalization of studying a group through its Cayley graph. So if you have a generating set, you're studying the uniform measure on the symmetric subset. And this formality allows you to consider in a nice way what would be like infinitely generated Cayley graphs, or Cayley graphs in which you give different weights to different generators. Okay. And nice objects to study are harmonic functions. So in this discrete setting, harmonicity is defined by satisfying a mean value property. So the value of f at a given point G is going to be equal to its average around this point, according to the measure mu. And particularly, we will be interested in the space of bounded harmonic functions, okay? So without entering into much details, this is a very nice space of functions. It's a Banach space. You can actually endow it with some operation that turns it into Banach algebra. And you can imagine that this connection will allow you to use tools from functional analysis, for example, to study the geometry of your group. Okay, so understanding this space is turns out to be very useful. So in this context, I will not give precise definitions. There is an object, a universal object called the Poisson boundary, which is by construction or by definition a probability space on which the group acts. That has two main properties. The first one is that the probability measure nu of the Poisson boundary is stationary with respect to mu. Being stationary, you can think of it as a dual condition to being harmonic, and it basically means that when you move the measure nu through the group elements and you average this action, then you recover the measure nu. Okay. And this Poisson boundary is going to satisfy that you have a representation of bounded harmonic functions as bounded measurable functions on the boundary. Okay. So understanding the space of bounded harmonic functions is the same as understanding measurable subsets of B. And a particularly interesting situation is when the Poisson boundary is trivial. By construction, this is if and only if infinity is trivial, which due to this isomorphism is the same as saying that all bounded harmonic functions on G must be constant. Okay, and the Poisson boundary will be non-trivial when you're able to show that there are non-constant bounded harmonic functions. Okay. So a bit of history, so where does all of this come from? The theory of Poisson boundaries for groups originated in the work of Furstenberg in the 60s. And since then, well, Furstenberg used it for proving rigidity results for lattices on semi-simple D groups. So very briefly, you have two lattices on two different semi-simple D groups. You want to compare them. So you want to say that in some way the lattice remembers the ambient Lie group on which it lives. Harmonic functions is a way of recovering that information. Actually, that's what Furstenberg shows. Since then, it has been used in many rigidity results. And maybe more in the line of topics of my talk, Using Poisson boundaries, you can actually detect many geometric properties of the group. For example, you can detect amenability, which is equivalent to the existence of some measure which we have Poisson boundary. If you know that the group is finitely generated, you can detect whether it is virtually nilpotent, which is equivalent to having every measure with trivial boundary. And for example, you can also detect exponential growth. Okay, for example, if you're able to find mu such that some finitely supported mu has non-trivial Poisson boundary, then your group must have exponential growth. So these theorems are actually useful. It's not just characterizations, abstract characterizations that really used. Particularly the first ones, there are classes of groups for which amenability has been proved using this characterization, for which no other proof of amenability is known. Or for example, in the third one, showing that a group has exponential growth, even though it's such a very basic concept, it's not that easy, right? There are not that many methods to show exponential growth. One of them is, for example, showing that, for example, you can find some free semigroup inside of your group. But well, of course, not all groups have free semigroups inside, even if they are amenable. Yeah, you could have torsion amenable groups. How do you show that they have exponential growth? One tool that you can use is try to find some non-trivial harmonic functions, okay, for some finite supported mu. Anyways, the question of today's talk that I want to focus on is a question about continuity of the space of bounded harmonic functions that I will make precise in a few slides, but I want to motivate that from the beginning. So how sensitive is this space when you do small perturbations on the measure mu? Okay, very natural question, I think. So I have not defined what the Poisson boundary is, but I will show some illustrative examples that will hopefully make things clear from now on. Main example among non-amenable groups are free groups, of course. Here, the main starting point is this very beautiful fact, and not trivial to prove, that also goes back to work of Furstenberg, that says that whenever you fix any probability measure on the free group, there's going to be a unique stationary probability measure on your Gromov boundary. Okay, so the free group is just words on A, B, A minus 1, B minus 1. The Gromov boundary is infinite reduced words. For any way that you define on how to average on the Cayley graph, there is a unique way to average on the boundary. You can think of it that way. So this gives you a natural candidate for what could be the Poisson boundary. It could be just the geometric boundary. And it turns out that with work of interesting work of many people, we actually know that this is the case with some extra condition, namely the finiteness of this Shannon entropy h of mu. Okay, I will speak about entropy more in a few minutes. So if we have this condition, then we know that this space parameterizes all bounded harmonic functions. However, it's important to remark, and I will not detail much into this, but this is very important. Will not be true in general if you look at measures of infinite entropy. So if your measure is very, very spread out or very uncertain to how it samples elements, actually you will get, you could in principle get more bounded harmonic functions than the one that are encoded on the geometric boundary. Okay, so this is a theorem of this year of Kunal Chawla and Josh Frisch. Kunal is speaking later today, but not about this result. But yeah, so this was very unexpected. People expected this to not be the case, but yeah, they give examples. So this situation for rather non-amenable groups. For amenable groups, the prototypical example are wreath products. Okay. So a wreath product is constructed by taking some group of lamps and a base group. Here, for simplicity, I decided to take the group of lamps Z mod 2Z, and the base group is going to be anything. And the wreath product is by definition taking direct sum of copies of the group of lamps indexed by the base group, and then to just take an extension by the base group where it acts by translations on the lamps. You might have heard of these groups also called as Lamplighter groups. The idea is that a group element basically has the information. You have to imagine that the group B, the base, is some street with lamps at every group element. Each lamp can be in a different state, on or off. And when you multiply by lamp elements, because this corresponds to some person at this position X changing what the lamp value is at that point, and multiply by an element of the base corresponds to moving this person around, so this position X, without changing what the lamp configuration looks like. Okay, so these are lamplighter groups. If the group B is amenable, they will be amenable. And we also understand relatively well how their Poisson boundaries look like. So in particular, if we choose some probability measure on these lamplighter groups, again with finite entropy, then non-triviality or triviality is well understood. In fact, the Poisson boundary will be non-trivial if and only if, when you look at the projection of the measure to P, so you just care about movements in the base and you forget the lamps, you want this projection to define a transient random walk, meaning that it comes back to the starting point. When you do a random walk, it comes back to the starting point finitely many times, almost surely. This is for non-triviality, that is existence of non-constant bounded harmonic functions. With a few more hypotheses, one can actually show that one can actually exhibit what this Poisson boundary looks like. So for example, if the measure mu is not only finite entropy, but say finite support or even a finite first moment, then you can show that there's going to be some stationary probability measure on this space of lamp configurations, so direct product of copies of Z mod 2Z, such that this probability space is the Poisson boundary. So it parameterizes all bounded harmonic functions. Yeah, so this is also a combination of work of many people. And the best result today is to George Frisch and I a couple of years ago. And maybe here one can already remark that this situation is really very different from the one of the free group. Remember, in the case of free groups, something very characteristic about it is that you have unique stationarity on this geometric boundary. Here we also have some type of geometric boundary, which is a space of infinite lamp configurations. But here, by no means will we ever have unique stationarity, right? As one can argue, for example, by amenability arguments, in general, there will be multiple stationary measures on such spaces. Okay, so geometrically, the situation is very different. Okay, so these are two examples to keep in mind: free groups and wreath products. So free groups think of their chroma boundary. Lamplighter groups think about lamp configurations. Okay. So I started speaking about entropy. So you have to think of the entropy, Shannon entropy of a probability measure, as the average amount of information that you obtain when you sample a group element according to mu. And the main interest is to study these quantities that one can define an asymptotic quantity associated with it, which is this asymptotic entropy, which corresponds to looking at the Shannon entropies of convolutions of mu. So this is, if you want to think in terms of random walk, is doing n steps of the random walk, seeing what's the uncertainty here. This quantity is going to grow at most linearly. So the limits over n as n goes to infinity is called the asymptotic entropy, and I use this lowercase h to denote it. And there's this beautiful theorem of Aves, Derianik, and Kajmanovic-Vershik, which states that all of the information of whether the Poisson boundary is trivial or not, that is, whether there are non-constant solutions to non-constant bounded solutions to harmonicity, it's all encoded on one numerical value, which is this asymptotic entropy. So this is going to be equivalent to the positivity of this number. Okay? So this is one reason to care about the value of h of mu. You have this very nice theorem. There are other reasons that I will maybe not enter into much detail. So for example, this h of mu is also related to the house of dimension of some harmonic measures on geometric boundaries for example, for Fuchsian groups. Yeah, so in some classes of groups, you want to see some action on some natural geometric boundary. You want to understand stationary measures there. H of mu will allow you to well, for example, to compute their house of dimensions. So you could use it to distinguish two different measures in this class. You can also use the exact value of h of mu to, for example, if you're doing a random walk on your group, you will have theorems of the style of Shannon, Macmillan, Brayman, if you've heard of it, which will tell you how spread out your random walk is at time n, asymptotically. Anyway, so I'm saying this to motivate the question of studying the value of h of mu. And more precisely, this is the question that I want to approach in the time I have left, which is this quantity continuous on mu? So fix your favorite group G, consider sequences of measures mu, mu k, suppose that they have finite Shannon entropy, and suppose that mu k converges to mu. So in these cases will mean that you have pointwise convergence of the values of mu k, so the masses converge. And we're also going to ask for the Shannon entropies to converge. Is it true that the asymptotic quantities also converge? Okay. So the second condition is implied by the first one if you ask more for the measures, for example, if they are all supported on a common fixed finite subset. But in general, when you allow them to be infinitely supported or you don't ask much more, you need to ask for the second condition, right? It doesn't make much sense to ask for continuity of the asymptotic quantity if you didn't have continuity of the one-time quantity. Turns out that in general, the answer to this question will be no. You don't have continuity in general. And yeah, maybe I will mention a bit some example in a few minutes. But yeah, so we will start speaking about results now. Okay. So the first result that I want to speak about is concerns to some extent the non-amenable situation. And it says the following. So the first paragraph is just the context. So we're asking this continuity question. We have this convergence of mu k to mu. And we're going to suppose the following. Suppose that there is a Polish space, so a completely metrizable space X, which models all of these Poisson boundaries. So all of the Poisson boundaries of mu and mu k can be realized on the space X endowed with appropriate stationary measures. Then, if you have a weak star convergence of the measures on the boundary, then this will in fact imply the convergence of asymptotic entropies. Okay? So this result in principle may look nice, but this could be tricky, right? Because we want to understand convergence of some quantities and we reduce it to convergence of some other quantities. So for this to actually be useful, one needs to argue that the first condition, this convergence of measures, is easier to verify than the second one, right? This is the only reason why such a theorem will be useful. It turns out that in many cases it is, because a very simple argument shows that if your model for the Poisson boundary is not only a poly space, but rather a compact metric space that emits unique stationary measures, then you always have this weak convergence on the left. Okay, so in any such situation, you have immediately continuity of asymptotic entropy. So this is nice. I will maybe just say one word on the proof. I will not explain it completely. I will just say that the main component is this formula of Kamenovich-Vershik, which tells you that this quantity asymptotic entropy, you can actually compute it on the boundary by averaging these quantities called KL divergences, which measure how much the measure on the boundary is changes when you push it forward through group elements. Okay. Anyways, let's not get into the proof. Some applications, direct applications of the previous result together with results of identification of Poisson boundaries are, for example, to hyperbolic groups or acylindrical hyperbolic groups. In these cases, well, in fact, the result was already known at the same generality I told it before, but with much more complicated proofs. So what's nice about what I presented in these cases is that it's a very, very short proof, very simple. And if you go into any of these references, it will be really, it's hard to read. Okay, so it's really a different proof and much more technical. Some new classes of groups covered by this result are, for example, SLTZ. So you have linear groups here. Here the result is new, even for finitely supported measures. And also some classes of groups acting on cat zero spaces with some contracting properties. Okay, that I will not detail because I am not a cat zero person. Okay, so this is the situation again for rather non-amenable groups, right? Everything I've said here is non-amenable. Turns out that when you go to the amenable realm, things are immediately much more difficult. So sometimes people tend to think that amenable groups are easier. Like, sometimes for questions, they are really more challenging. There's less structure. And in particular here, this is an example due to Anna Escher, which shows that on a grid product of Z mod to Z with base group, the infinite dihedral group, you can actually find this continuity of asymptotic entropy. So I think I will maybe not explain in detail this example, but it basically relies on showing that on this grid product, you can find a sequence of probability measures that have trivial Poisson boundary and hence zero asymptotic entropy, and which converge to a probability measure that has non-trivial Poisson boundary, hence positive asymptotic entropy. And well, of course, this is a counterexample for continuity, right? You cannot have a sequence of zeros that converge to something positive. And the thing that makes everything work is this observation due to Lorentz-Gilch, which is actually very simple, but I think it's a cute thing to know, which is that on the infinite dihedral group, whenever you do any finitely supported and non-degenerate random walk, this is going to be recurrent. It's going to come back to the origin infinitely often. This is very different from what happens, for example, on Z. On Z, symmetric random walks will be recurrent, but it's very easy to make it transient just by putting some weight to some side, right? What Gilch says here is that on the infinite dihedral group, there's really no sense of direction. And so even if you try to make your random walk non-symmetric, it's going to symmetrize itself. Okay, and this cute observation really is what's behind this discontinuity of entropy. Okay, so when I saw this example for the first time, I was not very happy because I really like grid products, and yeah, it was kind of weird to me that a counterexample to such a nice intuitive property, such as continuity of entropy, could be found among grid products. I wanted to understand this better, and so I did. So this is the last theorem I would like to speak about today, which says that basically asymptotic entropy is going to be continuous whenever you have, say, a grid product over a virtually nilpotent group that has at least cubic growth. Okay, so in particular, Z mod to Z with ZD, where D is larger or equal than 3, will have continuity of asymptotic entropy in the most general possible setting. And this somehow says that the previous counterexample, which remember was on the infinity, these groups have linear growth, is to some extent some low-dimensional phenomenon that really relies on this property of being able to get recurrence on your base group. Okay, so I have like 1 minute left, so I will just say a couple of words on the proof. The proof is very different to the previous theorem I explained, in particular because at this level of generality, we do not have any idea of how the Poisson boundary of these spaces is going to look like. Remember, I told you how Poisson boundaries of grid products look like for finite supported or finite first moment. Here, we're not supposing anything like that. And what we're going to use is that the entropy of the random walk at time n, well, entropy is information. You think that you are moving along the random walk. How do you save information on your group? Well, you're lighting lamps, right? So you can think that you are coding a message in the lamps that you are lighting or not lighting. So your entropy, your amount of information, is going to be directly related to how many distinct points are visited by the random walk up to time n. And once you've made this connection, well, it's a long proof, but part of the proof is showing that the number of distinct points visited by the random walk on the base asymptotically is also a continuous quantity on mu. Okay. So I guess I will leave it there. Thank you very much.
Okay, let's thank the speaker for his talk. Does anyone have any questions for Eduardo? Any quick questions? Well, I guess we have 4 minutes. Okay, so no questions?
I had one, maybe very stupid. Are there examples where like that there is convergence, but that like all the mu k are supported on like all the Poisson boundaries for the mu k's are on some space, but the Poisson boundary for the other is on another space? It's maybe a weird question.
Yeah, I mean, this is like a degenerate case of your question, I guess, the case of the infinite hydra group in the sense that the mu k's have trivial boundary, so you can suppose that they are
I know,
supported
but
on a one.
say you also have convergence, for example. Like say you also have convergence of the
Of
Abet's
the entropies.
entropies.
Yeah, I guess the answer is no, but also maybe for lack of examples, in the sense that most situations where one is actually able to describe the boundary fall, for example, within these classes of groups that, well, they do all have like the same space on which you can model the Poisson boundary. So yeah, I mean, examples in which we are actually able to compute the boundary are also examples which behave particularly well. So it's difficult to get examples as the one you say. I don't think there are.
Okay, thank you.
Mhm.